Okay. Bob, are you with us?
Yes, I am.
Okay, excellent. So I'm uh, unfortunately, due to a scheduling conflict, uh, involving bears, I guess. Uh, Bob Ergun, our next speaker, is in the middle of the woods in Yosemite, and is able to, but somehow is able to, like, guess, there's internet ports in the trees now, or something like that, and can tap in. So he's going to be delivering via Zoom, so he'll be a disembodied voice, and we just worked out that during his talk, he'll have sort of five kind of break points for us to break in and take questions, and I'll run around with a mic because of the Zoom. You'll need to definitely talk into the mic in this case to take any questions during his talk. And if Bob, could you give one of the things exercises we did was we did an elevator pitch for our ourselves. Just give a 1 minute introduction to who you are and what you do, and then you can
Okay.
get and then start with your talk.
All right. Well, I was unprepared for that introduction, but I'll give it an attempt. Hi, everybody. Good morning. I'm talking to you remotely, and I apologize for not being there in person. My name is Robert Ergun. I am a professor in the Department of Astrophysical and Planetary Sciences in the University of Colorado. I guess the most, I have built instruments on 8 different NASA missions that have gone from everywhere, the Earth's magnetosphere, Mars, solar wind, toward the sun. Um, and my basic uh, motivation will be explained to you in this talk. I am mainly a physicist, and I really like to understand the plasma physics processes that go on. All right, so with that introduction, which I was unprepared for, let me tell you what I'm going to talk about here. I'm supposed to be talking about the foundations of heliophysics, but I'm going to try to give you some motivation here. I'm more of a plasma physicist, while some people want to understand how the sun works, or some people want to understand how interacts, or how Jupiter works. That's fine. I love that. I'm more, I want to understand how the basic processes of plasma physics work in the universe so that we could understand how the universe works. And that's really what my motivation is. And so I'm going to give you a physics-based point of view, and this is my point of view, okay? And so that might be a little different than what you've heard earlier, but that's great. That's what you need to hear. Okay, so I'm going to first start off with a little bit of a motivation here. Why would anybody study heliophysics? Well, the basic idea of heliophysics is that, in my opinion, we can actually study some very fundamental, very important processes of the universe in situ. We could go there. We aren't just looking at light at this point in photons and trying to surmise what's going on in that area. We're actually sending spacecraft, making in situ measurements, and understanding these processes. And some of the processes you've already heard about, for example, magnetic reconnection, turbulence, particle acceleration, radio emissions, solar and stellar winds, and shocks. These are very fundamental processes that really drive a lot of plasma astrophysics, and are common to laboratory plasmas. So let me just start by going back in history a little bit. Well over many centuries ago, the people knew about the aurora. You could see it from the ground. But it was about a century ago, or a little bit more, that people really started, or scientists started to understand this process of acceleration. Once they understood that there were electrons and ions, and you could see in these striations, the magnetic field lines of Earth are being mapped out. So this is a particle acceleration process that is accelerating electrons into our atmosphere, and when they impact the atmosphere, they light up. So this was one of the, I think this was from my point of view, this is one of the beginnings of heliophysics. It wasn't until 1990s, which was, many decades later, that we put in satellites into the auroral zone of Earth, and that's where a lot of our first satellite missions went, to understand that this was electron acceleration. But we also discovered 3 separate acceleration processes in the same region, one being a acceleration of electrons down towards the Earth, one being an acceleration of electrons back away from Earth, which you don't really visibly see because they don't light up the atmosphere. And then finally, a third process called alphanic wave acceleration. And each of these processes is very important, and ends up being a very important acceleration process in other regions such as solar physics and in, say, supernova shells. Another early mystery that came about was cosmic rays. Physicists found in their cloud chambers, and that they were seeing particles streaking through their cloud chambers. This was the beginning of particle physics, the very beginning of particle physics, and it really wasn't answered. Well, cosmic rays still partly answered by shock acceleration, but it wasn't until heliophysics work, where we had satellites actually observe collisionless shocks, that scientists were able to then, surmise how cosmic rays were being accelerated in supernova shells. Another early mystery, and you've probably heard more about this from the earlier speaker, is the solar and stellar winds. When there were eclipses, scientists could see the corona and the stellar winds moving off of the sun at that time. This has been going on for centuries again. And it wasn't until we really started putting spacecraft up and understanding the nature of the solar wind that we were able to actually fully understand what is going on with these stellar and solar winds and how they drive a lot of the processes we're seeing at Earth and Mars and other places. This is ongoing work, and as you know, Parker Solar Probe has reached its closest approach to the sun, so this is a great time as far as spacecraft missions are concerned in heliophysics, and because we have this fleet of spacecraft that are making these types of in situ measurements. Another early mystery were solar flares. Now, you've heard a lot about that one, but this was a mystery at the time. We would see these, maybe this wasn't centuries ago, but this was 50 years ago, several decades ago, that we started seeing these flares from the sun, or noticing them in the X-ray. And again, what was going on? These things were erupting in 100 seconds, whereas we just didn't expect that kind of speed in over the distances being traveled in the sun. This led to these flares, led to the discovery of magnetic reconnection, or the whole beginning of a very big science. And magnetic reconnection now is known to happen at Earth, happen on the sun, occur in many astrophysical locations. And I'll talk a lot more about that later on. So this is ongoing work, and we now have a fleet of 4 satellites that are flying in a tetrahedron formation called MMS. And these have been studying magnetic reconnection in detail, the kinetic detail of magnetic reconnection. So this is my motivation in why to do this is because we could start to go places, go right in situ and understand some of the most basic processes. Another one would be collisionless shocks. It was first believed, believe it or not, that we couldn't have shocks in plasmas because they were collisionless. Yet, this observation clearly shows a shock front in front of a star in with a high flow interstellar medium. It wasn't until we got spacecraft to really verify these at the Earth's bow shock, and now we can really take a very, very close look at the incoming solar wind reflecting from the bow shock, and then gyrating back into the Earth. That we start to understand the complexity and the details of a collisionless shock. So, another one, we see radio emissions from the universe. Some of these came from Jupiter, and the Jupiter radio emissions were one of our first indication that something was going on with magnetic fields, because these are at the gyro frequency of the electrons at Jupiter. And we're starting to see that before we saw them coming from Earth. And eventually, when we put satellites up and went into the generation region of these radio emissions, that we discovered this idea of the electron cyclotron maser, which is now known to be very, very active in producing a lot of radio emissions from the Earth, from Jupiter, Saturn, solar flares, binary systems, and many, many astrophysical systems. So another one, I could go on and on here. Turbulence. We're now looking at a very, very turbulent environment. Plasmas are inherently turbulent, and that's simply because mostly they do not have collisions. But there are cases, such as the surface of the sun, where collisions are active, yet we still have turbulence. We know there's turbulence in water and on Earth, but there's a whole new ongoing work of collisionless turbulence, which is a different animal altogether from what we see in our environment. So these are the type of things that are going on, and this is my motivation. We can do, in a nutshell, we could do a lot of fundamental physics by going and looking and making measurements in situ in our heliosphere to understand the processes that are going on in the broader universe. So I'll stop here, take a break, and accept some questions.
Any immediate questions on what Bob has said so far? We got one.
I'm sorry, if you can get back to, I mean, it's not like a scientific question, it's mostly asking for a reference. So I never worked with fast data, and I never knew that there was such good pitch angle resolution for particles, for electron precipitating particles, for example, from fast. So if you can maybe suggest some papers to read about that. Specifically for maybe monoenergetic precipitations.
Oh, right. Most of these papers were published. The best one would be by McFadden et al. FADDEN, and there is also a book by Poshman called Auroral Plasma Physics that has a lot of these same pictures in it and a lot of this information. It's an ISI book.
Okay, thank you.
Any other immediate questions for Bob? Going once, going twice. Okay, so no questions in the room right now.
Okay, so I'm going to go on to the next section and give my view of plasma physics. And this is my view, the way I approach plasma physics, and the way I would normally when I teach plasma astrophysics, how I would approach teaching this in a class. My view of plasma physics is it's just a bunch of ions and electrons floating around in space. They're charged. And if you look at a plasma, this is what you see. If you look really close enough, you'll just see a bunch of dots moving all over the place. So the basic idea is, how do we start solving a problem like this? And there are three really fundamental approaches to plasma physics, and each of them has their own role. The kinetic approach, which is on the upper left, is basically, let's follow every particle of the universe, calculate its motion, and then we can, because we know where every particle in the universe is and what their charges are and how they're moving, we could calculate E and B and then calculate how they're going to move. And this is called the kinetic approach. This is the most rudimentary kinetic approach. It is very accurate, of course, because we're making very few assumptions in the beginning, but it is absolutely unwieldy. One obviously can't follow all the particles in even a closed system, even in a small system. But we do have these things called particle in cell PIC simulations, which make a few assumptions now, but very few assumptions, and can follow this. And we also have the approach with distribution functions and other areas where we're going to keep full information on the particles, both their position and their velocities, so we could understand their motion. And that would be called kinetic plasma physics. Now, for each of species, electrons, ions, there might be different types of ions, such as protons, helium, double plus, etc. We can form basic three different numbers, bundle them up into three different numbers that are a function of space only. And one is the density of that species, which we'll call N, the velocity, and U is really, when in my writing, when I use V, it's the velocity of a particle. When I use U, it's the velocity of a fluid. So this would be a fluid velocity and a temperature. So we have these three things: density, velocity, temperature. And we could figure that out or calculate those for any given B and E, and then we could calculate B and E from Maxwell's equations if we know these fluid velocities and densities, etc., from each species. Finally, we could put all these species, bundle them all together into a single fluid, and just calculate the overall density, velocity, and pressure, along with E and B, using MHD equations. So MHD is the most useful, but the least accurate of all of the methods. And kinetic is the most accurate, but not as applicable or tractable. So plasma physics are, we have a little ongoing joke that if you are in a physics department, you generally do kinetic physics because being wrong is a cardinal sin, but being useless is okay. Whereas most astrophysicists like MHD because they could actually write papers, and being wrong, well, nobody will prove it. So you have a choice between being useless or wrong, but that's just our joke, because we like to use all three of these methods. All right, and they're all got their own use and their own place. For large scale problems, we're going to use MHD. To understand a small scale, localized region, small region, and understand the detail, we'll go to kinetic or multi-fluid. All right, so with kinetic, we basically start with distribution, try to follow particles. And that's what a particle and cell simulation does. It's primarily, instead of using all the particles, we're going to have one one particle represents, say, 1,000,000 particles, so that we're not overwhelming our computer with, too many particles to follow. And this is actually becoming more and more promising, because with the amount of memory we have, for example, back when I started PIC simulations, well, I mean, we were lucky to get a megabyte of memory and put in 1,000 particles. And now we're looking at putting petaparticles in, 10 to the 15th types of particles. And these are really answering questions a lot better. Of course, in each and every one of these, we need Maxwell's equations to understand how to calculate E and B. So a self-consistent solution means that we follow the particle motion, we calculate E and B, and then we subsequently follow the particle motion, then calculate E and B. You could see how you're bouncing back and forth in a simulation from this. The heart of a kinetic is distribution functions. I'm assuming most of you've seen these. This is basically the number of particles per unit velocity and unit distance, or unit volume, or unit velocity in phase space. And the most well used and recognized of those is a Gaussian or a Maxwellian. But I should tell you that plasma physics is moving away from Gaussians and Maxwellians unless there are collisions, because almost everywhere the distributions are non-Gaussian. They're more close to kappa distributions, which I might talk about later. We could reduce these distributions. We call that reducing, to calculate densities, velocities, and temperatures, or the average energy per particle, which will end up being temperatures. And that is, we could do that in 3 dimensions. And this allows us to follow the motion kinetically, and then go to something we can measure, measurable quantities like density, velocity, and temperatures. So the multi-fluid approach just starts with these reduced values, the density, the velocities, and the temperatures, which are reduced. We're not looking at the full phase space. We're not looking at where they are in their velocities, individual velocities anymore. We're just looking at the density, how many particles are in any given cubic volume, and the fluid flow and their average energy. We can still make a lot of progress with this by calculating for each species, following the motion of the fluid, and then calculating the E and B, or the electromagnetic forces, from using Maxwell's equations. And then finally, these are bundled, and you've seen this before, and into a single fluid, where we combine the ions and the electrons. In this simple case, there's just 2 species, but you could do this with more than 2, where you'll take the density, which is in the upper right, and you'll just average the density and velocity and the pressures from each of the species. Interestingly, you could also calculate this current, and then we'll end up with our continuity equations, our force equations, frozen in conditions, Ampere's law, Faraday's law, and we will end up with a simple but very, very useful and tractable set of equations called magnetohydrodynamics. Now, what I try to emphasize to everybody is that magnetohydrodynamics makes 2 assumptions. One is the principle of quasi-neutrality. It says that the number of ions and electrons for calculating fluid motion only is the same, but not necessarily for calculating electric fields. But we do not derive electric fields from a density difference. And the other is that the particles are frozen in to the magnetic field, or gyrating about the magnetic field, and they only have free motion along the magnetic field. So these assumptions limit the accuracy of MHD to large-scale events, but it's turned out to be a very, very useful formalism. Now, personally, I use all 3. I like MHD to start a problem. So often when I solve a problem, I will start with MHD and work it backwards. And if I see a small scale region where MHD may not be accurate, then I'm going to jump back to multi-fluid or kinetic work to understand that just that region where the MHD may not be valid. So often we work backwards. We go MHD to multi-fluid to kinetic, depending on the problem and what we need. So you must have, I always say the best heliophysicists are going to have all three of these tools in their toolbox as much as they can. All right, so I want to, as a last comment in this section, I would like to talk that there is a large, very, very important and large difference between how we approach problems in a collisional environment versus collisionless. Now, we're all used to living in this collisional environment. That's what we live in. The air you're breathing has 10 to the 20 molecules in every dice-sized region, and they're colliding all the time. This, from the central limit theory, forces them into a Gaussian or Maxwellian and forces them to share their energy equally. And this makes a large difference in the momentum exchange and how we would approach the problem. So they often lead to Gaussian distributions as per central limit theorem. And for example, the interior of the sun is collisional. A planetary ionosphere is collisional. So we treat these differently. When we get into these very low density areas, such as the solar wind, the corona, the Earth's magnetosphere, and almost all mass astrophysical plasmas, except for those closest to the central object, collisions do not occur. They do not play a role. And the momentum and energy exchange is regulated and dominated by the electromagnetic fields. And due to low plasma damping, there's very little damping. These are often turbulent plasmas, and they often have non-Gaussian or non-Maxwellian distributions. So this is an important difference that we have to make. Now, partially collisional plasmas, you're right in between. All right, so I'm going to stop here and take some questions.
Questions for Bob on this last section?
I know you mentioned that you might talk about this a bit later, but I'm interested in hearing more about the kappa distributions instead of Gaussian for like solar wind distribution functions, because I hadn't heard of that before. I've mostly seen papers using Gaussian or like bi-Maxwellian or something like that.
Yeah, that's a very, very good question. Kappa distribution, now Gaussian distributions and Maxwellians have been, well, Maxwell was in the 1800s. So you could instantly see they've been around for centuries. And there is a idea of the central limit theorem. And for all practical purposes here on Earth, when we're looking at a fluid such as water or air or anything that's highly collisional, a Gaussian is all you need. But the kappa distribution is a little bit more complex. In a limit, there's a kappa function. In a limit, it becomes a Gaussian. But as you get the kappa factor will tell you how the tail of the distribution. In other words, we get this accelerated tail particles on that. Now, there are books on it. I don't know. Are you familiar with Python, by the way? I should ask first. Or you use Python there?
Yeah.
That's a yes. Yeah, I mean, you could get that there are Python routines that will give you kappa distributions. they are much more unwieldy to deal with analytically, but it turns out that there are certain problems such as acceleration and turbulence and dissipation where these are more important. It's important to distinguish between when you're kappa-like and Maxwellian-like. I think there's a lot more, when I read the literature, a lot more people are using kappas now when we're in collisionless plasmas. But I think the Maxwellian distributions are still most widespread usage. Does that answer your question? I don't know if I did or not.
Yes, and we've got a few more questions, so I'm just going to be passing around the mic.
Okay.
I guess whenever I see this distinction being thrown out as such a binary kind of like treatment of the plasma, whether they're collisional or collisionless, I always wonder about the corona, because it seems like in some literature it is treated more as like this very collisionless plasma. Some cases, some people treat it as a collisional. Is there such a thing as a hybrid plasma? Are people doing theory or formalism with that? Yeah.
Well, yes, and clearly, this is always the case. When we have a collisional plasma, we could put in terms such as viscosity and resistance into our momentum equations and force equations, etc. And they will very properly, if there is a high enough collisions. Now, what is a collisional versus collisionless? My definition is if the mean free path of an individual particle is larger than the region that we're looking at or examining, then you could treat that region as collisionless. If that means that your average particle is not going to collide with anything within that region. If the mean free path is smaller than the region that we're studying, then we could say that it's collisional and they'll dominate. Now, doing a hybrid is often difficult because treating it with our known viscosity, you see the difference between collisionless and collisional formula in analytics, that collisionless will not have viscosity or resistance in it. Instead, it will have to depend on the electromagnetic fields. Whereas the collisional plasmas or fluids that we treat would have those two terms. There aren't very many good analytical descriptions that do weakly collisional plasmas. As far as I know, you could still do them via simulation, MHD, etc., but the use of the viscosity and the resistive terms is not accurate in that regime, but that's the best we can do at this point. That's a very good question, by the way. Very good. And by the way, we have the same problem in ionospheres. As you go lower and down in the ionosphere, the atmosphere it's actually the neutral collisions start to dominate. And there is obviously a gray zone where it's neither collisional nor collisionless. Okay.
And
I hope that answered.
Yep. And we have a couple of more questions.
Hello. I wanted also to ask about the kappa distributions. So do we know from observations how long these kappa distributions can be remained? So let's say you have a population and you describe them by a kappa distribution with a certain kappa value. Do we know how long the distribution will, or this population will stay in this state?
Well, first, to begin with, the kappa distribution doesn't always fully accurately describe the real distribution. It's one of the best approximations. Now, how long it will stay in that state? The answer is where you are. If you're in a collisionless environment, such as the Earth's, say, magnetotail, where the mean free path is 1 astronomical unit, okay, it's even longer. It's like 2 or 3 AU in the magnetotail, and the size of the region is 1 part in 10 to the 6th of that. So you cannot expect a collision to happen. that kappa distribution will remain for virtually ever, for a very long time. So the treatment is that's the way it will remain. Okay. That's its most settled state at that point because it's the electromagnetic fluctuations that are going to dictate its shape, not the collisions at this point. Now, there are some theories that claim that electromagnetic fluctuations will lead to these kappa distributions and that should be its remaining state or final state. I'm not 100% sure that these are that rigorous, but this is all a very, very good approximation. Another very good question, though. The central limit theorem won't apply to these kappa distributions until the short answer is until you have a sufficient number of collisions or sufficient number of actions that would share the energy equally and form a Gaussian. Does that answer your question, or you're asking very good and hard questions on me here, challenging me?
Yeah, so my question is also about kappa distribution. I'm sorry.
Oh my goodness. I opened up a
I
can of worms.
so okay, so from the basic so does the intuition for kappa distribution only arise from MHD and not from hydroturbulence, where collision is important? And the second question is, there are other models that describes the distribution of I don't know what exactly the distribution, but I assume they're the distribution of velocity and magnetic increments that are not Gaussian. I mean there are different models, and then how do we differentiate between, in your point of view, how do we differentiate between different models?
Well, in the real world, for example, I can go back to this example here where we were studying the distribution functions. I don't know if I have a picture of it. We will look at the distribution. It's measured, the electron and the ion distributions. Now you can see there's a tremendous tail on this distribution. Let me just talk. The top two panels are ions going from about a few electron volts to almost a million MeV, so many orders of magnitude there. And these distributions have tails on them. So we'll measure them, and then we will try to fit them to some sort of model so that we can analytically analyze. And often it's the kappa distribution that fits the best. Gaussians do not fit. I could tell you that right now. So our approach basically is region by region. We do not have a general approach to, this region's Gaussian and this region's, one type of distribution fits all plasmas. Now, this is a highly collision-less regime, so we have virtually no collisions going on, and you'll have very, very active tails on the distribution. Now, there are other types of distribution functions, and the reason we want to fit it to begin with is so that we can theoretically work on it through some sort of analytical model. Do you see that? And MHD doesn't necessarily predict that, but we could then modify our MHD equations or our multi-fluid equations so that they're accepting the kappa distribution, that we're putting that information of that tail and the non-Gaussianity of the distribution into our formalism. Now, if you're using a PIC simulation or a kinetic, you're done. You don't even have to assume what type of distribution function you have. I don't know if that answers your question, but yes, there are a lot of different ways of mapping distribution functions. And this is a ongoing, a lot of ongoing research in our field is trying to analytically model these collisionless distributions.
Okay, I think we'll save the other questions for later, and we can move on to the next section.
All right. I always do this quick review because Nick wants me to do this, so I do it.
Oh, yeah.
The review of particle motion and adiabatic invariance. I'm not quite sure that this is going to be so quick that I hope most of you have seen this before. I just simply want to point out that we really, rely on, when we look at particle motion in from a kinetic point of view or just from a fluid point of view, we really rely on the Lorentz force. And the Lorentz force is nothing but Newton's law. There's nothing different from that. And the first thing that everybody should know, and hopefully I'm not making a bad assumption here that you do know, is that if you were to solve this equation with a magnetic field, you'll find that the motion of the particle will simply gyrate along a central point that is free to move along the magnetic field line, but if in the absence of a imposed electric field, is simply frozen in to its magnetic field line. So let's introduce the concept of a field line, which can be introduced as long as B doesn't go zero anywhere and there are no parallel electric fields. So if you start easy with electric field equal to zero, you could just see the particle going around in circles, kind of gets dizzy. That's the frozen in idea. Now, if you were to apply a finite electric field to this plasma, you will see very quickly that it drifts in the x direction at a speed of the electric field in the y direction divided by b, which I'm putting in the z direction. So in this case, I'm simplifying the problem, putting the electric field in the y direction, b is in the z direction, and the particle will drift in the x direction. Now this, you may say, oh, well, the particle's drifting. Well, we're going to, the most intriguing point of this is that if you go into that particle's frame and you start moving in the x direction at exactly this Ey over Bz, and you were to measure the electric field, it would be zero. So the particle's going into a frame in which the electric field is zero. And that is the frame of the magnetic field as well. We call the rest magnetic field frame. So if you were to think of a field line, that field line is basically the particle is stuck to its field line. Okay, and that's called the frozen in condition, which is really the heart of, really an assumption in MHD. So you have this general drift equation, which is that the electrons or ions will drift in the E cross B motion. And then you could do this with a force, a gravitational force. And I will say there's a whole host of other drifts, which I'm not going to go into because I think just it's time-wise, we can talk about the curvature drift, the grad B drift. Those are very important in reconnection. But we have to introduce these other types of drifts that are actually violating the frozen in condition because those are important. All right, so that's the single particle motion part of that. And I didn't introduce adiabatic invariance, but what happened to my slide? I don't have adiabatic invariance, so I'll take questions on this. If you want to ask about adiabatic invariance, I'll try to answer it. How's that for quick?
That was fast, yes.
I've earned my pay now, Nick. Okay, that was what I'm supposed to talk about.
Yes, we'll send you the check in the mail. Questions on single particle motion or adiabatic invariance? I'm sure a lot of you have seen some of this before, but it's always good to have a level set for everybody and put everybody in the same framework.
My thinking is that the idea that the magnetic field also drifts into a frame where Ey equals zero, because if you go into this frame of Vx, you will find that EY goes to 0. Now, a lot of people don't get that in their head, but the electric field is frame dependent. If you actually move through a magnetic field, you will start to see an electric field, or a change in the electric field as a minimum. So the plasma likes to stay in the environment where E is 0. So that's
even without relativity, they move from one to the other.
Well, that is relativity. Maxwell's equations are already relativistic.
Right. Yeah.
So.
Any questions on this section? Going once? Going twice? Okay, I think we can move on.
Okay, let me see what my time is here. I got 45 minutes, right? About 40 minutes?
Yeah, you got about
Okay.
you got 45 minutes.
Okay, no worries. I'm going to try to end on time. All right.
Yes, thank you.
Okay. So my next section, this is why I was shifted the particle motion, is I want to talk about I'm going to talk about two of the most, I think, important and fascinating phenomena or physical processes that are widespread. And they're in the sun, they're in the solar wind, they're in the magnetosphere, they're at Jupiter, they're at Mars, and they're in supernova shells, they're in accretion disks, you name it. We are going to have shocks and magnetic reconnection. And these are, I think, some of the most important and most active approaches. And this is where heliophysics scientists have made an incredibly strong, contribution to our understanding, because we have the in situ measurements. So let me talk a little bit about the basics of shocks. These are very, very important processes because they really are universal. And I like this picture. It is a shock. It is the idea is we have such a shock around the Earth. The reason I like this picture is sometimes when you look at the shock from afar, it makes more sense than when you look at it up close. And all we have ever done is look at it up close at Earth. But this is from far away. There's a star and there's an interstellar motion of the plasma. And basically you get a shock. Now that yellow line there is where the shock is heated up. It's radiating. So this is a highly radiated shock, but you can see this plasma, which is cooler. This is an infrared picture, by the way. Shocks and then radiates right behind the shock where it has tremendously heated up. You can see these little shocklets all around as well in this region. And you can see another one up here. I don't know if you can see it in the corner. So this is not a random or, scarce or odd phenomena. In fact, this is something we see very little. Now, the shock has this curved structure. Now, the idea is our sun also has this type of a shock. It's pointing towards Alpha Centauri. And as you may or may not have known, that Voyager spacecraft have crossed into the vicinity of this shock. It's kind of still, it's a very far away, and it's going to take a long time to fully penetrate into the interstellar medium, but it is certainly seeing that type of shock. So with that idea, there's another type of shock that occurs, and this is a supernova shell. So this is a nebula, but the idea is in the center of this, you'll find a neutron star, a pulsar, that I don't know in this particular event, I'm sorry, I forgot, but it's on the order of thousands of years ago, a star went supernova. In doing so, it has blasted a circular shell. Now, we don't see it from our side, but you're seeing a nearly circular shell. It's not very well formed, but the central star exploded and this supernova is moving outward. in another, if you give it another 100,000 years or so, it will have dissipate into the medium. There clearly is large amount of turbulence in this supernova shell. And what is converting, what's going on with these shocks is they're converting the RAM energy from that explosion, meaning the particles are just sent out almost at the speed of light. And it's converting that energy into thermal and magnetic energy. And again, what you're seeing is the radiation coming out of the shock zones where the plasma is compressed and greatly heated. As the shock moves into the interstellar medium, it gathers up all the plasma there and the magnetic field and just starts pushing it outward. So this is where these are hypothesized to be the root of most of the cosmic ray acceleration in a galaxy and in the universe. So how do we begin with shocks? We begin with the idea of magnetic pressure. Now, I've written down the MHD force equation, which I know the earlier speaker has talked about. And the idea is that you have the force terms here. This is the convective derivative, the time derivative of u. So this is just Newton's law. This is the grad pressure. But the main thing is this magnetic field force. It's the b squared over 2 mu naught. That's the gradient of it. This is a curvature force of the magnetic field, and this is gravity. So let's assume this shock is already in steady state and it's not slowing down or speeding up. Gravity's negligible. And for the most part, let's just assume B is straight, although that's a kind of rather poor assumption, but let's do it for now. You'll only be left with two terms. And that's the grad pressure and the grad of the magnetic field squared. Now, this is called magnetic pressure for a very simple reason, that if you look at it, this is the particle pressure. The P is the particle pressure. B squared over 2 mu naught is the magnetic pressure. And you can see that a very simple idea comes up, that the gradient of the sum of those two must be zero. So that means that the particle pressure and the magnetic pressure are constant. So again, this makes the assumption that there is no curvature in B, because this term becomes active if there's curvature. So in a shock area, we often start by assuming the magnetic field is straight for the time being, and then deal with curvature as a perturbation or a secondary problem. You may have you can have a very high pressure plasma here with low magnetic field, or you could, and on the other side here, we could have a high magnetic pressure with low particle pressure, and you'll find that these two are in balance. They're very, very happy. Because the pressure, this sum, particle pressure plus b squared over 2 mu naught, is a constant. So this is a good way of dealing with thinking first out of the box with with a constant. Now there's another term in this equation, which is this term here. It is a convective term. It's the density times the velocity, the fluid velocity dotted into the gradient of the pressure. It's called a convective derivative. This has ram pressure. Okay. And if you think about ram pressure, there's two ways of thinking about it. One is compressible, and 1D, which is a plasma physicist thinking, in that the divergence of rho u is constant in the continuity equation. So we could just take this rho u and put it inside this gradient here. Because if there's no time derivative, the divergence of rho u is equal to 0. So why can't we just commute that with the derivative? And that's fine. And we end up with this divergence of rho u squared. That's energy. That's ram pressure. Rho u squared. That's mv squared. There's a 1/2 particle missing in plasma physics. So we often will call this value here, rho u squared, the ram pressure. This is the, for example, if you're standing there and somebody's spraying a water hose at you, the force of that water that you're feeling is ram pressure. It's not thermal pressure, it's not magnetic pressure, it is the momentum of that water hitting you. So if I were to spray you with a hose, that you could feel ram pressure. Now, speaking of water, Bernoulli's equation has a 1/2 in there, and a lot of people get confused on that. And that is because it's incompressible. So rho is constant in this case. Okay, so we could move the rho inside here, but we need to put a 1/2 since we're taking a gradient of u squared. That will give you the 1/2, that will remove the 1/2 factor. So this is Bernoulli's equation. And that is something, so these are two extremes of an incompressible versus a compressible in 1D. This is more exact and useful in our real world. This is more useful in plasma physics. So a lot of people get confused about that factor of 1/2 from Bernoulli to a ram pressure. So what happens at a shock? Well, a shock, you have ram pressure in almost all those cases I've shown you. Let me go back to this first case. You have pressure, the interstellar medium ramming into this area, and that is the water hose pressing into this. What it does is it has to be balanced by the pressure, thermal pressure, and the magnetic field. So we can interchange these three as long as we keep them constant. So often in a shock, the ram pressure is so high that it will compress the magnetic field and the plasma, which is frozen into it. And this then produces the reverse pressure to stop the flow, or at least slow it down. Okay, so that's the best way to think of the simple way to envision a shock is ram pressure, particle pressure, magnetic pressure, have to sum to a constant. The ram pressure is basically forcing this particle and thermal pressure to increase. It turns out that shocks occur very, very at sharp boundaries. So at the Earth, the solar wind is ramming towards the Earth at a very high speed and forms this layer in front of it called the bow shock, just as you see in these early pictures here. It's just the same idea. It's curved on a gross scale, but by the way, on a fine scale, it might look more like that. But nonetheless, we have this idea of the high-speed solar wind being slowed down, and in here there is a higher thermal and magnetic pressure, but lower ram pressure. So we can look at the Earth in the sense that the solar wind plasma is going to come in. We will often call that upstream, the upstream region of a shock, as U1, velocity 1, density 1, magnetic field 1, and pressure 1, which means upstream. And then this is the downstream value. And these can be what we call high Mach. In other words, they're traveling so fast, they're traveling faster than the speed of sound or faster than the Alfvén speed. And in this case, this is the dominant term. It's mostly ram pressure of the solar wind coming into the Earth. Once you go past this shock, which is a very abrupt and thin layer, you end up with, well, a little bit of ram pressure left over. You end up with a lot of thermal pressure and some increased magnetic pressure. Now, this plasma is going to divert. It doesn't form a shock around the Earth's magnetosphere. And basically, the standoff here is the ram, by that point, since the flow is diverted, the ram pressure is gone, and the magnetic pressure of the Earth's magnetosphere is probably going to dominate. Now, this gets trickier because, of course, this is a bent field line, and we have to actually deal with that more carefully. So in MHD really can't describe the inside of a shock. It's a very thin layer, and it really violates a lot of our assumptions of MHD. You'll really need to go to kinetic or to fluid theory to understand the detail in here. But we found very simply by just using conservation equations that we can model shocks with what are known as the Encke-Huguenot jump conditions. The idea is the amount of material moving into the shock, which is the density times its velocity, on the upstream side must be the same going out of the shock if we're in steady state. Otherwise, we'd be gathering up plasma here, and at one point this thing would get bigger and bigger or more dense and dense. And that is not what we're assuming in these cases, since when we vision our Earth, our bow shock, it's there for a billion years or something, so it's not gathering plasma. So that means that we could relate the density going in or the amount of plasma flowing, the number of particles per square meter, the mass per square meter going through the shock must be the same exiting it. So that relates this downstream velocity, which is slower, and the density is higher. So this is lower density, higher velocity goes into higher density, lower velocity. The magnetic field's frozen in, so we have the same formula for the magnetic field. This is our pressure equation. This is ram pressure, particle pressure, magnetic pressure on the upstream side must be balanced by the ram pressure, particle pressure, and magnetic pressure on the downstream side, assuming we're in the shock frame. If this weren't balanced, the shock would start to move somewhere. Now, the third one I'm not going to go into. This is an energy equation. All that says, and it's far more complicated, is that the amount of energy flowing into this shock must be the same as going out of the shock. Okay, so you could immediately see that this fourth equation can be violated somewhat if you're radiating or sending energetic particles out of the shock, but it's still a very important equation. Now, I've written these equations for a perpendicular shock, or what is known as a quasi-perpendicular shock, meaning that the shock normal is perpendicular to B. So we do not have B threading the shock. There's a whole much more complicated set of equations with cosines and shock angles, which one would deal with more accurately later. All right, so let me show you some early. This is 1977. Whereas really when we first started measuring these shocks, and this is the solar wind side, and this is the density, and you can see the density somewhere around 10 or 11 or something like that. And immediately in this very thin layer, the density just jumps by almost a factor of 3, about 3.5. So it just jumps. At the same time, the velocity goes down. This is the solar wind velocity at 300 kilometers per second. This is probably cubic centimeters per cubic centimeter, particles per cubic centimeter. It just decreases. Well, that's exactly what our equations tell you, is that the density on the velocity on the upstream side is high, the density is lower, and we're going to slow it down, but we're going to compress it. So this is equation 1 doing the exact same thing. Equation 2, here's the magnetic field. It jumps by about 3.5, a factor of 3.5. So that is our second equation. Now, the third equation can also be balanced if I were to show you temperature, but that is actually more complex. The temperature actually jumps more than a factor of 3.5. It jumps a large amount, and that is predicted, as predicted by these equations. So this simple approach of the Encke-Huguenot jump conditions allows us to very, very quickly model and set the scene for a shock, but it's not telling us what is happening in here. MHD can't do that. That is got to be going to kinetics. Now, there's a lot of work that has gone on and is still ongoing on exactly what's happening. So what I'm going to show you is just this region in here, only it's backwards. And I apologize. This is the upstream side, and this is the shock. The downstream side, it's the density's jumped. You see the density is just, boom, jumped. Now, if you look at it, wow, there is a lot of action going on in here. The magnetic field is not just, well, we could even see a hint here that the magnetic field doesn't just smoothly rise and is all happy. In fact, it's very turbulent downstream from these shocks, and they're non-Gaussian distributions downstream quite a bit. You could see that the magnetic field simply has this edge, and it jumps up. There is a tremendous amount. I can't tell you, these are extraordinarily large electric fields that are oscillating in waves going on during this shock, in this shock. There's also an electric field, a shock potential, an electric field that is pushing the electrons from going in. Sucking the electrons in and stopping the ions, because the ions have larger gyro radio and tend to penetrate deeper. On the upstream side, you're seeing this is a function of angle. At 180 degrees, you're seeing the solar wind, and that 180 degrees is towards the sun. So the ions are coming from the sun right into the shock, and you can see them starting to be peeled off and reflected. So the ions are now starting to peel off in other directions, and these are the reflected ions, which only go out so far because they turn around and go back into the shock. Okay, and if you look at different pitch angles, you'll see different views of these reflected ions at all pitch angles, whereas the solar wind ram flow is just hitting right into the shock. By this point, the shock has already occurred, the temperature's gone up, is not in equilibrium, is left in a very highly non-equilibrium state. You end up, one sees turbulence downstream for quite a while after that. So we're just starting to understand this whole idea reflected, or we have understood it. If you look at it in a velocity space, this is the x velocity, which is from the sun. You can see the negative x velocity here. That's the solar wind ion beam coming in. This is the z velocity in this case, because we're looking in the xz plane. You're seeing these ions absolutely coming about and reflecting. This is the first set of reflected ions from the shock. This is the second set of reflected ions. These are reflected twice. They went back into the shock and bounced off. And then this is the third. So you're seeing these layers of reflected ions in the shock. So this is a very, very complex kinetic process that is very, very well modeled by these jump conditions. So I'm not going to go too much more into details, other than to say that a shock, while it looks very clean in these pictures, like this picture is an artist's rendition, but this picture here is you might think, oh, that's a very nice little shock. If you were to look inside on how the sausages are made, so to speak, it is not as pretty as the MHD picture or the jump conditions. But I want to say these jump conditions work remarkably well to predict average downstream conditions versus average upstream conditions. So that's the way you start the problem. I like shocks because this is the way you do plasma. I do plasma physics. I start with the MHD, understand the big picture, and then I'm going to go into this small layer here and try to understand what's going on in that layer. And you find a much more complex kinetic situation. And this allows us to understand these reflected ions are very important for particle acceleration. They are very, very high energy, they're very fast particles. Not all the ions reflect, a lot of them just go punching through, but they are an important aspect of how the shock actually stops the ion flow, the solar wind ion flow upstream of the Earth. So I'm going to stop here and have a question session.
Okay, other questions for Bob? We got one.
Hi, I just want to ask, like, in shocks which have drivers, like interplanetary shocks. So in these
Yeah.
shocks, okay, sorry. So in these interplanetary shocks, so what could be the conditions for their evolution? Like once they form, so are they become driverless, or driver itself have some conditions to drive that shock further, or they just become driverless and depend on the interplanetary conditions?
Okay, well, so it's important when we study shocks, we go into a shock frame. Okay, in all these cases, in the Earth shock, it's easier because the shock frame is really stuck with the Earth. And these jump conditions are assuming that the shock's not moving. So in order for these to apply, in an interplanetary shock is moving. So we must move along with that shock. We must transfer our frame. And in that frame, for the most part, and I'm just going to say this with tongue in cheek, that the once the shock forms, the upstream conditions are pretty stationary. These are very, very quasi-stationary events in the sense that the only thing that's happening is really inside this shock layer. And in the frame of an interplanetary shock, you would see a high RAM or a high Mach type flow coming in from one side, and a lower speed flow and a higher density and compressed magnetic field come in from another side. Now, all we have to do in MHD is balance these three terms in the jump condition. That's what the jump condition does. It balances those three terms, plus it balances energy, which is an important concept. But all that must be done in the shock frame. So when you ask that question, yes, shocks can evolve, but we assume they evolve much more slowly than the transit time through the shock. Okay, so the first step is you go to the shock frame. The second step is you do these jump conditions to understand what it's like, but you have to move the shock frame. And then the third step, in my opinion, is go into and understand this region. But there's another step, is that if this shock evolves or changes, for example, in an interplanetary shock, the amount of ram pressure might change in time slowly, but that changes much slower than the transit time through the shock. So you would treat that as a perturbation. Is that what you asked?
So it means that they become driverless with the time.
Well, I'm not sure what driver means. You always have to have your driver to have this compression and the energy release. Not becoming driverless.
So once a shock is formed by the help of the driver, and it's evolving with its own energy, right?
Right. Once the shock is formed, it's evolving with the energy. There's a constant quasi-steady state. I say quasi-steady very importantly, where you have the high energy, high velocity particles ramming into the shock from the upstream side and the low velocity coming out. And energy is conserved in that shock. The amount of energy entering from one side goes to the other, but that's in the frame of the shock. To be very careful that you don't do this outside of the frame of the shock. It will not, these conditions are in the shock frame. Okay, so I don't know I generally don't call it driverless or driver, but as long as we have this high RAM flow, this shock will exist. If the RAM flow were to suddenly turn off, it would lose its driver, the shock would dissipate. Okay, but I'm not sure how that happens, because this is moving outward away from the sun, typically interplanetary shocks.
All right, we got at least one more question.
Okay.
Hello. I believe on the next two slides you showed these substructures of shocks like foot, ramp, over and undershoot. And I wondered on slide, was it on the next, 45? Do you know how people define or identify the foot of a shock? And
Oh,
I guess not all shocks have a foot.
I was hoping nobody would ask that question. From my understanding, and this is, I'm trying to recall. Okay, so the idea of the foot was that the shock is supersonic and super alphanic in this case. So no information can travel upstream because the velocity here, 300 kilometers a second, is far faster than the alphane or sound speed. That means it's kind of like a fish swimming upstream. If it's swimming at 5 miles per hour, but the water is going at 10 miles per hour, it is actually going downstream, okay, in your frame. And so the idea was nothing could happen in front of the shock because the information can't get there. But there are waves called Whistler waves and fast mode waves that can actually travel slightly upstream. And that was the idea of the generation of the foot. All right, now when you look at a lot more detail, it's not as clear what the foot is because there is this slight increase in the density and slight increase in the total magnetic field, which is the black line here, right in front. And it's believed that this is sort of the magnetic foot here. And that's really caused by Whistler waves and other types of information that's being sent upstream faster, but by very high speed waves, but they're not dominant. Once you get to this magnetic edge, all of a sudden we're erupting into turbulence. And now it becomes much more difficult to describe exactly what's going on because you've got to understand that this is really much more of a turbulent plasma. And here's kind of what you would see in this picture here as the density has a small ramp. Now, this is a very narrow region. This is basically one ion gyroradii. In other words, the ions, this is an ion gyroradii out here, or somewhere here. The ions can't gyrate any further out than this. So you're looking at just one ion gyroradius here. And the ions are being scattered by this electric fields and by the oscillating magnetic fields. So we end up with this sort of strange distribution function right upstream of the shock. So if you ask me about what these regions are, the ramp and the foot, they were defined earlier, before we looked too carefully at these things, and we could still sort of see them, but they really are taking on different character when we get out our magnifying glass and look at very much closer. It's not as obvious in this picture, but I would call this the ramp. You see that right there, where the density suddenly jumps up, although it's already previously a little bit of jump up here. And none of these regions are cut and dry. There are shades of gray in here. Does that answer your question?
Yeah, somewhat. So I understand it's more complicated.
Oh yeah.
Yeah. Okay, thank you.
One more question. One more question.
Hi, Bob. Thanks. So I understand that these quantities are conserved across the shock, but it seems to me that these would be conserved across a smooth transition too. So I guess I'm curious about why we get a shock and why we get a shock in such a localized region. Like what sets it to be there in such a localized region?
Ooh, that's a really good question. Why don't they spread out more? Well, the answer, I think, is the fact that you have to think of it as, say, an airplane coming in. Airplanes form shocks if they're going supersonic, right? This plasma up here has no idea that it's going to run into something at this point in time. There's no information at all that can be sent up to this region. In fact, the only information can be sent is about a gyroradius in length. The ions carry the information back upstream to tell this plasma to start slowing down. So think of it as information theory. this is my thinking of it. It's probably going to get poo-pooed by shock experts, but that's okay. I see when I look at these data, I see, well, there's a little bit of information slowing this thing down right here. But again, those are not your alphane or your sound waves, which are your fast mode waves. They're not the main MHD waves. They're more of a kinetic wave that is only transferring a little bit of momentum up here. What really happens is the massive amount of momentum transfer, that is going on, has to go on in this ion gyroradii region, and it's one gyroradius of a energized ion, the ion with the energy of the solar wind. So it's really not the ion gyroradius itself; it's the ion gyroradius if you take the velocity of the solar wind and divide it by the magnetic field, etc. So this is really a good explanation of why all this action seems to happen in one or two ion gyroradii. It's because the ions have to be the ones that carry the information back. The waves, they're starting to act here. You can see the waves, but they really can't. Again, think of that fish trying to swim upstream. They're going at a much slower velocity than coming downstream. So it's not until this thing starts to slow that the waves can travel upstream and create this mess. And so it's sort of a self-consistent circle. You're not going to be able to have this long drawn out shock, because how are you going to get the information upstream? Okay, and to draw out the shock, what is going to carry that information? The waves can't do it. Well, some Whistler waves can, but they're very minor. The electrons certainly can't do it because their gyroradius is too small. So it really ends up being the momentum transfer and the information of slowing this solar wind ion beam down is really being carried by the ions. Does that make sense?
Yes, thank you.
I'm not sure that was the best answer, but it was more of an intuitive answer.
Okay, great. Thank you. So why don't we move on to the last section? You've got about 10 minutes left in the
all right,
allotted
yeah.
time.
It always ends up being this way. This is magnetic reconnection. All right. If you, most of you, I'm pretty sure the previous speaker talked about this, so I'm just going to show this very quickly. You have magnetic field pointing one direction, the other direction. This is called anti-parallel magnetic reconnection. There's an electric field that is driving the plasma down from this top and up from the bottom. These two lines reconnect. I have to start the thing over again. And you get these high-speed jets going out the in the horizontal axis on this direction. The main problem with magnetic reconnection is not really how to have this inflow and the outflow. It's really what is called the diffusion region of magnetic reconnection. So the main physics that we're interested in, that I'm interested in anyway, is this region where we're breaking B. We're taking out a pair of scissors and cutting the field line and rejoining this, the hip bone to the bottom one to the top one to the bottom one. So this is really the enigma in physics. And how does this happen? Now in MHD, it's called the diffusion region because E plus V cross B can't be zero. You can't be frozen in anymore. That's very clear. And so it was thought early on that there must be a diffusive process. In other words, a collisional process. But magnetic reconnection is seen in collisionless plasmas. So this started, the solar flare puzzle was really what started all of this. And in the 50s, it was noticed even earlier on, but it really became heated scientific research in the 50s, that solar flares erupt in about a minute. So we're talking about 100 seconds, 10 to 2 seconds. If you were where they are in the corona, there are some collisions, but if you were to calculate the magnetic diffusion time across the magnetic field lines due to the collisions, it would take, I think this is a little exaggerated, it's an old slide, but 10 to the 14 to 10 to the 16 seconds. Okay, 10 to the 2 is their actual speed. 10 to the 14 to 10 to the 16 was predicted. Even for an astrophysicist, 14 orders of magnitude or 12 orders of magnitude is too much. For a physicist, they would just drop dead on the floor. So the idea is that we can't use this resistive term at all. So how are we going to break the frozen in condition without a sufficient number of collisions? Again, if we use the collisions, we get this very, very large time scale. What happened with at the same time, just a few.
Right.
So I'm not going to be able to really finish this other than to tell you that this magnetic reconnection problem, where I was, we saw it in the solar flare puzzle. We saw it in the Earth magnetic reconnection. How do auroras start? Tokamaks. Believe it or not, we love magnetic reconnections in space plasmas. The fusion people hate it. To this day, it is one of the major problems with getting controlled fusion, because magnetic fields love to reconnect and it always crashes their tokamaks. It's in the magnetorotational instability around accretion disks. It is seen in gamma ray it's probably central to gamma ray bursters, pulsar nebulae. We see it in the solar wind. Gosling et al. Has reported this. And it is a genuinely universal process. So again, there's this 12 orders of magnitude time problem. And this is when reconnection, we started looking at all the terms in generalized Ohm's law. And I'm going to make this long story short. We ended up looking at the Hall term, which is this term here. All right. Is that better?
There we go. Yes, now we see it.
All right.
Great.
So here I was talking about magnetorotational instability, gamma ray bursts, pulsar nebulae. I'm sure you guys could read them all really quickly, right? Anyway, the whole point is that there was two steps. First, it was recognized this Hall term plays a role, but only for the ions, decoupling the ions. So now magnetic reconnection has two diffusion regions, one called the ion and the other called the electron diffusion region. And then PIC simulations started attacking this electron diffusion region. But I'll make a long story short, MMS in situ measurements actually solved, I think, this puzzle of what's going on with the electrons, in the sense that they have these agyrotropic, what called crescent-shaped distributions. You can see this red crescent in the parallel perp plane, which meant that it's an off-diagonal term of the electron pressure. Meaning, this is interesting. This is a tensor, and we're normally used to thinking of temperature and pressure as a single value, but it's actually a temperature, and there are off-diagonal terms. And that is a very, very great solution to this puzzle on exactly what's going on in the electron diffusion region. So a lot of advances have been made in both the subsolar and tail reconnection. And again, this is an image of what happens in our magnetotail and how we make measurements. And I will stop at this point here because I'm out of time. So I almost made it for you, Nick.
Okay, excellent. All right. Final questions for Bob. Yep.
Hello. So,
Yeah.
from your experience, are these discontinuities, be they jumps across a shock or anything related to reconnection or any other discontinuities, are they apparent discontinuities at MHD scales? Meaning that if you were to zoom in far enough to kinetic scales, you would actually see a smooth rise or decrease of the quantities? Or are there processes that are truly discontinuous, no matter how far you zoom in?
To answer that question, it's a good question. Again, you guys are really good. In MHD, the idea of having a smooth, a jump, a discontinuity is one thing, but I would say it's the opposite. Often what we see in MHD, I'm going to go back to shocks because I talked about that more. So just bear with me. Often what you see in MHD is something like this, where you see kind of a transition, a jump. But if you look really carefully, it's not a smooth transition inside. It is actually a very, very gnarly, turbulent transition at small scales. So again, this whole picture here in this slide is just a little snapshot of this little region here. And it is the inside of this red bar here. So yeah, the answer to your question is when we go to different scales, we see structure at all scales. That's the short answer.
Thank you.
Okay.
My question will be about reconnection. So in the Earth's magnetotail, how local is this reconnection? Is this something that MMS can answer
yeah.
already? Or like maybe configuration is a bit complicated for MMS to resolve that?
Well, what happens in magnetotail reconnection is very local. But as you know, from what we see, there is a scale. There are subscales and a lot of structure in there. And just to go through this again, the MMS satellite is at 20 RE, at minus 20 RE right here. And what happens in the magnetotail is the magnetotail acts like a misbehaved child. It says, I'm not reconnecting. And magnetic field starts building up and goes, no, I'm not going to reconnect. But all of a sudden, too much excess magnetic pressure builds up and it will suddenly explode in reconnection. And when it does that, the current sheath thins and then the magnetic reconnection offsets. And this region is very, very highly structured, but there is a single region where there is an electron diffusion region. It is on the electron scale size, electron skin depth size. And what happens is that with MMS, we are fortunate in that these all retreat tailwards. The magnetic reconnection, once it occurs on Earth, is blowing out a jet this way, which is stopped by the Earth, and this way, which is not stopped. So the whole region itself goes down tail, and it will go right over top of our spacecraft sometimes. Not always. It could go above it in Z or below it in Z, but often we do see it go right past us. And then, so we're actually scanning this reconnection region from tail side to Earth side due to its motion, not to our motion in the spacecraft. And this is a scan. This is such a scan in this picture. Now you can see it's highly structured, but I want you to look at the blue line in panel G. It's negative, meaning that the jet is going anti-earthward. We're seeing the ions being jetted right at us. And then all of a sudden they're going earthward. It is right at this point where the arrow says flow reversal where the reconnection site is. But look at the turbulence. If you want to try to make this out on what's going on, you really have to start understanding turbulence. Reconnection and turbulence are almost 100% linked in almost all the observations. Sometimes we see a clean, smooth reconnection site, but rarely do we see that. Does that answer your question about jump and
actually
scale?
a bit more interested in dawn-dusk sort of dimensions of this reconnection.
Oh, that's the length of the X line.
Yeah.
Oh boy, that is an active question. From what I understand and see in the observations, I'm very suspicious that the X lines are not more than a RE or two long. Now, does reconnection occur tail wide? Yes, but it is chopped to pieces all the way across from dawn to dusk, in my view of looking at too much data. Does that make sense? Is that what you
Yes.
were asking?
Yeah, thank you.
Hello, hi. So my question is with respect to your page number 45. So in the ramp page number 45.
Thank you for getting that number.
Yeah. So in the RAM region and in the food region, if we see generally, we observe uh, electron-driven modes such as whistlers and ion-driven modes such as lower hybrid waves. So what do you think that how does these wave electron-driven or ion-driven waves influence or changes the dynamics of the background plasma? I am asking with respect to plasma diffusion and plasma
Right.
transport.
Well, a lot of the waves are very, very important. In particular, the electromagnetic waves, probably fast motor alphanic, that are in this region here, they're reflecting. As the ion comes in, it's gyrating, but it's seeing magnetic fields in different directions now. Ion 1 will see a magnetic field in one direction, and ion 2 will see it slightly different. So they're not going to gyrate or in the same fashion. They're going to start scattering. Do you see that? So these waves are extraordinarily important for that region, and particularly these low frequency magnetic waves. Now, the higher frequency electric field waves are more acting on the electrons. They are basically thermalizing what is an electron, the electrons, and heating them up and absorbing some of the free energy of the ions and transferring it to the electrons. So these waves play a very important role. And as you could see, just looking at this data, this is not something that we could easily just cleanly set up and say, oh, here's a formula, this is what happens. This is something that we really need to take a lot more look at to fully understand. And I will say there's a lot of literature on shocks, and they are better understood than I am making it out. Does that
Okay,
help?
thank you. Yeah, thank you.
All right. Nick, isn't there a general question session after this?
We are in the general question session right now.
Oh, okay. So, all right. I was just wondering what role I'm playing here. Isn't Marco going to come in?
He's here. I think what we decided was that we've got a couple of different things going on right now. So I want to continue with you to about 12:05,
Okay.
and then we've got some other things that are happening then.
Okay, fair enough, because all my
Okay,
electronics
so-
are overheating at this point.
Oh, okay. Well, maybe we'll do one more and then see where we're at.
All right.
So my question is about reconnection again. And I guess something that has confused me for a while is like how this idea of current sheet like collapse by the Turing mode instability, how it interplays with like this, what you highlighted here, like the Hall term and the electron pressure gradient. So I was wondering if you could like comment on how these concepts
Well,
are at play together.
that's a good question, but let me just to clarify on this. Can you hear me? Okay.
Yeah.
To clarify on this, there are different scales. When you're hearing about the Turing mode, that is a larger scale. It is a larger scale process where the current sheet starts collapsing in a lot of cases due to overmagnetic pressure. And once that Turing mode sets off, it's going to create a thin current sheet. At that point, in the diffusion region, the kinetics start taking over. The Turing mode all by itself isn't going to cause the reconnection, although it's a very good way of describing it. The ions start to decouple first, and they decouple due to this J cross B term in the Hall, and they are not going to go into the center of the diffusion region, rather they're deflected. And then the electrons are going to have to go through this process whereby they develop non-gyrotropic orbits. So you're down to an electron gyroscale or electron skin depth scale at this point. So this is a different look. This is a look inside. The Turing mode is a much better look at the gross picture. And sometimes this reconnection is such small scale compared to the region, that the tearing mode will set up multiple X lines and multiple islands in this. And that's a very, very important part of the process of reconnection. So you have to look at them both. And I think what's confusing you is scale size. I'm looking in with a microscope, and the tearing mode would be looking at it with a much larger field of view. Does that make sense?
Yeah, I think that helps a lot. So, like, the tearing mode is invoked typically to explain the global timescales of the current sheet reconnection.
Right.
Is that
Right.
correct?
Yeah, that would be a good way of invoking it. Although the tearing mode does often involve some sort of resistance, which is the one thing that we need to really investigate thoroughly. But yeah, it's been entirely successful otherwise in looking at again, even the global picture is messy. Let me go down to this event here. Look, this actually formed a big reconnection blob and then quieted down, then formed another reconnection blob. So even at the tearing mode scale, you have multiple scale sizes of islands and reconnection regions. And then inside those multiple scale sizes of the reconnection, you have the Hall scale size, or the ion scale size, which is called the ion skin depth, C over omega pi. And then you have inside of that region the electron scale sizes. So this is very much a multi-scale process.
Can I just add a comment on that? So
sure.
I agree with everything you said, Bob. What I would like to add is the tearing mode exists as a theoretical model of an instability in which the disconnection, or if you like, the reconnection, or the loss of conservation of magnetic flux or change in topology can be triggered by all those terms that you described, and especially true for the electron pressure gradient. And this idea of the self-similar collapse and the aspect ratio, indeed, typically you start off from scales that are larger, but if you follow the logic of that carefully, you can actually even explain, for example, these strange times when you have electron-only reconnection or things like that. They can all be embodied, and I don't think tearing is the right word. These are reconnecting modes rather than tearing modes, because the tearing mode is, as I think the way you're talking about it, is the resistive tearing mode, and the s to the minus 3/5 scaling, which is what we usually refer to with the word tearing. So it's a more generalized idea of the reconnecting instability in different regimes.
Oh, I mean, you have to look at it. I'm looking from inside out. Tearing mode, you'd be looking from outside in, I would say, because you're collapsing down to the small scales. I'm looking at small scales moving out.
We agree.
And somewhere they meet. But I also will contend that you can't separate the turbulence. From my view, and just in situ measurements of these, there are very few cases where it's extraordinarily clean and can be described by, a analytic version. And that's the challenge, I really think, is understanding turbulence and how it interplays with this reconnection. I mean, that is a big future challenge.
Okay, Bob. Thank you so much. Any last words of wisdom for our participants?
I can give you words. I'm not sure about wisdom. I just want to thank you all for putting up and listening and asking such great questions. I really do want to thank you. And I would just say enjoy the rest of the summer school.